chapter 5. So chapter 5 is on discrete probability distributions. And so section 5.1 is in general talking about probability distributions, discrete probability distributions mostly. So in chapters 2 and 3, we looked at how to organize data into frequency distributions, and then how from there and that was in chapter 2, how to organize things into frequency distributions. Then in chapter 3, we looked at how to find the mean and standard deviation for frequency distributions. In chapter 4, in chapter 4, we looked at probabilities associated with random variables. Now, and in chapter 4, they assumed equally likely cases. In this chapter, we're going to combine the results of chapters 2, 3, and 4 so that we have associated probabilities with the random variables in a table, a probability table. And from there, doing something very similar to what we did with relative frequencies, we'll find the mean and standard deviation. And so it's really just combining everything that we've done in the past, like 3 chapters, into one. Once we've done that, we no longer have to assume equally likely cases. So in chapter 4, we assumed equally likely cases so that probabilities turned out to be something involving accounting, an exercise in counting. In this chapter, and for subsequent chapters, we will no longer need to assume equally likely cases, because now we can do things in general. So a random variable. So now I'll be able to define some terms a little bit better. So a random variable is a variable typically denoted by capital X. So random variables are supposed to be denoted by capital letters. I myself usually like lowercase letters than uppercase letters. So sometimes I'll write them uppercase, but a lot of times I write them in lowercase letters. So a random variable is some variable which has a single numerical value for each outcome of a procedure and is somehow determined randomly. Let's get a better definition. A random variable is a mapping. So notice it's a function. So a random variable is a function that assigns a unique real number to each outcome of the sample space. So it's a function from the sample space to the reals. Better definition. A random variable is a real valued Borel function defined on the sigma algebra associated with the sample space. So if we remember back in chapter 3, I think, when we did probabilities, or is it 4? When we did probabilities, 4 when we did probabilities, sorry, we just did it. Back in chapter 4 with probabilities, we defined a probability on a sigma algebra, and a Borel function is just a function so that you can define a probability. So that's what it means to be a Borel function. So it means that you can actually define these probabilities. You can actually calculate them for this particular variable. So recall, a discrete random variable results from a process in which you count. And so in general, your sample space is countable. A continuous random variable has values that are associated with measurements. So you're going to measure with a continuous random variable. In general, the sample space is uncountable. a shipment of 8 VCRs contains 2 defective ones. 2 VCRs are selected at random. Let the random variable X be the number of defective VCRs in the sample. Determine the sample space and list the values of your random variable. Well, you're going to pick 2 VCRs. So the first VCR could be defective. The second one could be non-defective. Or let's say first is defective and the second defective. The first one could be defective and the second one non-defective. The first could be non-defective, second defective. The first could be non-defective and the second could be non-defective. Those are the only possible choices that you have for picking 2 VCRs where you have either defective or non-defective VCRs. Let X count the number of defective VCRs. Well, there are no defective VCRs here, so X is 0. There's one defective, so you have X is 1 here. There are 2 defective VCRs, so X is 2 here. So my sample space is DD, comma DN, comma ND, comma NN. My possible values of my random variable are 0, 1, 2. Do one last example, then we'll start the exam. Flip a coin 3 times and let the random variable X be the difference between heads and tails. So find the sample space and the possible values of X. So you could have head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, tail, head, tail, tail, head, tail, tail, tail. And so that's my sample space. Let's determine the possible values of X. So difference between head and tail. So 2 games. Let the random variable be the number of games played. Determine the sample space and the possible values of the random variable. So suppose I'm a hockey team and you're another hockey team. So for the very first game, I can either win or lose. But once I've won a game, or you've won 1 game, neither of us have won 2 games. So we have to keep playing. So if I win the first game, and then the second game I win, we're done. Similarly, if I lose the first game and I lose the second game, then you won the first game and you won the second game. Therefore, you won 2 games, and so we're done also. So now, suppose I win the first game and then lose the second game. Well, each of us have only won 1 game. So we would continue with play. Similarly, if I lost the first game and you won the first game and you won the second game, I'm sorry, if I lost the first game and then I won the second game, then each of us have won 1 game. So we would continue to play. So now, suppose I win the first game, lose the second game. If I win the third game, then we're done because I've won 2 games. Similarly, I won the first game, lost the second game, but then on the third game, well, I lost, then again we're done because you won 2 games. You won the second and third game. So no matter what, if I win the first game, lose the second game, well, in the next game we will be done because either I will win or lose. In either case, one of us will have won 2 games. Now, suppose I win the first game. Suppose I lose the first game, win the second game. Either I win or I lose the third game. If I win the third game, then I've won both the second and third game, so we're done. If I lose the third game, well, then you have won the first and third game. So again, we're done. So this is my possible sample. This is my sample space. Win-win, win-lose-win, win-lose-lose, lose-win-win, lose-win-lose, lose-lose. That's it. Now, let me count how many games we have played. Well, 2 games, 3 games, 3 games, 3 games, 3 games, 2 games. So the only possible number of games that we have played is either 2 games or 3 games. So X is either equal to 2 or 3. So a probability distribution. A random variable X gives rise to a probability distribution, which is a set of ordered pairs where the first component, the first coordinate, is the value of my random variable. And the second coordinate is its associated probability. So a probability distribution is a description that gives the probability for each value of the random variable. We often express it as a graph or as a table or maybe some formula. So a discrete probability distribution. In a discrete probability distribution, the sum of all the probabilities are equal to 1. Every individual probability is between 0 and 1. So we have the following situation. For every value of your random variable, there's associated with it some probability. This probability can never be negative. You can't have a negative probability that you're going to get an A in this class. Neither is the probability greater than 1. You can't have a probability greater than 100% that you'll get an A in this class. And if you add up all the areas here, the sum of them will equal 1. So if you look at all the grades, well, there's a probability of 100% that you're going to get one of the grades, A, B, C, D, E, F, etc. So this type of diagram is called a probability histogram. So this is the probability histogram for the number of Mexican-American jurors among 12. So this is a visual representation where for every random variable, we have its associated probability. So this visual representation as a histogram for my probability distribution is called a probability histogram. So let's determine if the following is a probability distribution. So first, if I look here, well, each of these associated probabilities are all greater than or equal to 1. And well, greater than or equal to 0. And the sum of these, so 10, 20, 50, 60, 100. So the sum of these is 1. So therefore, this is a probability histogram. Since every probability is greater than 0, and the sum of all the probabilities is 1. A shipment of 8 VCRs contains 2 defective ones. 2 VCRs are selected at random. Let the random variable X be the number of defective VCRs in the sample. Determine frequency distribution for X, determine the relative frequency distribution for X, determine the probability histogram, the probability distribution of X. So, well, the first two of these we've done before. We figured out, we've determined frequency distributions and relative frequency distributions back in chapters, well, 2, 3, and 4. Now, the new thing is just to determine, in addition to that, a probability distribution. And we'll see that it's really very similar to what we've done before. Okay, so let's try to determine the frequency distribution first. Oh, good. So let me do this. So I have here a shipment of 8 VCRs. They can either be defective or non-defective. In this shipment, 2 of them are defective. So I have 2 defective VCRs. The rest of them are non-defective. So the other 6 are non-defective. I will pick 2 of them. So if the first one I pick is defective, then there's only 1 defective VCR to choose, but there's still 6 non-defectives to choose. If the first one that I chose was non-defective, then there's still 2 defective ones. But I've chosen one of the 6, so there's of these VCRs, non-defective VCRs. So there's only 5 non-defective VCRs left. Let me count the number of defective VCRs. And so if I do this, well, I have, let's say in this situation, I have 1, 2 defective VCRs. So I have 2 defectives. So X is 2. Here I have, well, let's say 1 defective and no defective. So X is 1. I have no defectives and another one. I have a non-defective. So I have a defective, non-defective. So there's 1 defective. I have a non-defective, and then the next one is defective. So I have a total of 1 defective. So X is 1. Here I have a non-defective followed by another non-defective. So none of the VCRs that I picked were defective. Therefore, X is 0. And so the possible values of my random variable are 0, 1, or 2. And let's see how many we have. Well, let's see. For 0, 6 times 5 is 30. For X equaling 1, 6 times 2 is 12. 2 times 6 is 12. Plus 12 is 24. Let's look for when X is equal to 2. 2 times 1 is 2. So I have a total of 56. Let's divide each of these by 56 to get my relative frequency distribution. So for X equals 0, 30 divided by 56. For X equal 1, 24 divided by 56. For X equal 2, 2 divided by 56. That is my relative frequency distribution. Now, let's try to determine my probability distribution. So, well, we have the same situation. We can have 2 defectives, 1 defective, or we can have no defective.
So either X is 0, 1, or 2. Let's try to figure out each of these probabilities. Well, 2 of the 8 are defective originally. 2 of the 8 are defective. The rest, the other 6 out of the 8, are non-defective. After I've chosen the first one to be defective, there's only 1 remaining defective out of the 7 remaining VCRs. So 1 out of the 7 are defective. The other 6 out of the 7 are non-defective. If the first one I choose is non-defective, then there are still 2 defective ones out of the remaining 7. The rest of those, 5 out of the 7, are non-defective. So let's figure out the probability that X is 0. 6 over 8 times 5 over 7 is 30 out of 56. Let's determine the probability X is 1. 6 out of 8 times 2 out of 8 is 12 over 56. 2 out of 8 times 6 out of 7 is 12 out of 56. So let's add these. So I get 24 out of 56. Lastly, let's figure out the probability X is 2. 2 out of 8 times 1 out of 7 is 2 out of 56. And now, and so that is your probability distribution. But now, if you look here, notice that these numbers okay, now I've made it really small. Notice that these are the same. This relative frequency and this probability distribution is the same. So it turns out that, here that if we have equally likely cases, then this probability distribution will be the same as your relative frequency distribution. So it's, well, things that we've done before. So now, of course, I don't necessarily have to assume equally likely cases. I can still construct this. So it turns out that if we're looking at the equally likely case, then what we've done with the relative frequency distribution gives us the same thing. But we now have a technique to where we don't need to assume equally likely cases, and we can still construct a probability distribution. Okay, so, this also has a diagram. So let me continue here using this. A married couple plans 3 children. Let the random variable X be the number of girls, B, the number of girls after the firstborn. Construct the probability distribution for each of these random variables. So we have, this couple has 3 children. So the first child can be a boy or a girl. The second, a boy or a girl. The third can be a boy or a girl. So we get boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. So here are the situations. So boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, 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 boy, girl, 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 boy, and girl, girl, girl. Those are the members of my sample space. So that's the sample space. Now, let's do part A. Let X count the number of girls. And so, let's count the number of girls. Well, boy, 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 no girls. Boy, boy, girl, one girl. So, boy, 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 no girls. So X equals 0. Boy, boy, girl, one girl. So X is 1. Boy, girl, boy, well, in this case, there's one girl. So X is 1. Boy, girl, girl, oh, well, in this case, there's 2 girls. So X is 2. Girl, boy, boy, well, in this case, there's 1 girl. So X is 1. Girl, boy, girl, well, in this case, there are 2 girls. And so X is 2. Girl, girl, boy, well, again, there are 2 girls. So X is 2. Girl, 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 so in this case, there are 3 girls. And so X is 3. So X is either equal to 0, 1, 2, or 3. Well, assuming girls are just as likely as boys, then we have the probability of getting a boy is 1/2, a girl 1/2, a boy 1/2, a girl 1/2, a boy 1/2, a girl 1/2. So the probability of getting boy, 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 1/8. Boy, boy, girl, 1/8. Boy, girl, boy, 1/8. Boy, girl, girl, 1/8. Girl, boy, boy, again 1/8. You're just multiplying. Girl, boy, girl, again 1/8. Girl, girl, boy, again 1/8. Girl, 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 again 1/8. You keep multiplying a half times a half times a half. So you keep getting 1/8. So let's figure out the probability X is 0. Well, there's one of these, boy, 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 which is 1/8. So the answer is 1/8. We have boy, boy, girl. So now let's figure out when X is 1. So you have boy, boy, girl, boy, girl, boy, and girl, boy, boy. Each of those have a probability of 1/8. You add those up, so you get 3/8. Next, let's figure out when X is 2. So you want 2 girls. So boy, girl, 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 boy, girl, and girl, girl, boy. So there's 1/8, 2/8, 3/8. And lastly, when X is 3, so girl, 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 just 1/8. And this is my probability histogram. Next, let me do part B. I want to count the number of girls after the first boy. So here I have the first boy. There are no girls. So X is 0. There are no girls. Maybe I'll just do it from here. So after my first boy, there are no girls. After my first boy here, well, there's just a boy. It says no girls. After the first boy, there's no girls. After the first boy, well, we never have a boy. There are no girls. So X is 0. After the first boy, so here's the first boy, well, there's 1 girl. After this first boy, there's 1 girl. After this first boy here, there's 1 girl. So X is 1. After the first boy, there are 2 girls. And this is all 2, 4, 6, 8 of the situations. So X can either equal 0, 1, or 2. Each of these, if you recall, have a probability of 1 out of 8. And so 1 out of 8 plus 1 out of 8 plus 1 out of 8 plus 1 out of 8 is 4 of them, is 4 out of 8. So the probability that X is 0 is 4 out of 8. Let's look when X is 1. Well, 1 out of 8 plus 1 out of 8 plus 1 out of 8 is 3 out of 8. Lastly, when X is 2. Well, 1 out of 8. Oh, there's still. Okay, so let me use this still. It says, oh, actually, on the other one, I have a diagram too. Okay, so let's go back. Yeah. Yeah, I have a diagram on this one too. Okay, so in a certain bias coin, a head is twice as likely as a tail. Oh, so this is not equally likely cases. A coin is tossed 2 times, and the random variable X counts the number of heads. Construct the probability distribution. Okay, so let's do that. So head twice as likely as tail. So I flip a coin and either get head or tail. But head is twice as likely as a tail. And so for every tail, you'll have 2 heads. And so 2 out of the 3 times you flip a coin, you get heads. Only 1 out of 3 times you get a tail. Actually, let me see if this looks any better. No, it's exactly the same. Okay, so next, after you flip a coin, you can either get heads or tails. Again, head is twice as likely as tail. So 2 out of 3 times, you will get head. 1 out of 3 times, you get tail. 2 out of 3, head. 1 out of 3, tail. And so I'm counting the number of heads. So I have here, let's look at my sample space. So first off, well, I can flip a coin and I can either get head and then head, head, tail, tail, then head, tail, then tail. And so if I do head, tail, tail, that means that I have no head. Tail, head, 1 head. Head, tail, 1 head. Head, head, 2 heads. Okay, so let's count. So here I have no heads, so X is 0. Here in these 2 situations, I have 1 head, so X is equal to 1. Here, both the times I flip, I get head, and so X is 2. Let's figure out the probability X is, so I have X is either equal to 0, 1, or 2. Let's figure out the probability X is 0, that you have no head. So 1/3 times 1/3 is 1/9. 1 head. 1/3 times 2/3, 2/9. 2/3 times 1/3, 2/9 plus 2/9 is 4/9. Let's figure out the probability you have 2 heads. 2/3 times 2/3 is 4/9. And that is your probability distribution. A wholesaler makes a profit of $50 on each item that's received from a manufacturer in perfect condition. If it is received in less than perfect condition, then the wholesaler loses $5 on each item. Let the random variable X be the total amount of profit on each item, and 0.7, the probability of receiving an item in perfect condition. Construct a probability distribution. So you get, so X here is the profit on each item. If, let's look at this situation here. If the item is received in perfect condition, you make a profit of $50. So X is 50. The probability of receiving an object in perfect condition is 0.7. And so the corresponding probability is 0.7. If it is not in perfect condition, then you lose $5. So X is -5, because you're losing $5. You're negating $5 from your profit. If there's a 70% chance that the item is received in perfect condition, there's a 30% chance it is not. And so the probability is 0.3. And this is my probability distribution. We found for families with 2 girls, the mean number of girls is 0.1 and the standard deviation is 0.7. Use those values to find the maximum and minimum usual values for the number of girls. Well, remember that the usual values are between mu plus or minus 2 sigma. And so the minimum usual value is mu minus 2 sigma. The mean, 1, minus 2 times the standard deviation, 0.7. So negative 0.4. The maximum usual value is mu plus 2 sigma. So the mean, 1 plus 2 times 0.7, 2.4. Obviously, and it's unusual if you have less than 0 number of girls. Okay, so identifying unusual result probabilities, so the rare event rule for inferential statistics. If under a given assumption, such as the assumption that a coin is fair, the probability of a particular observed event, such as 992 heads out of 1,000 tosses of a coin, is extremely small. Then we conclude that the assumption is probably not correct. It's probably not correct that if you flip a coin 1,000 times, that you're going to get 992 heads, and assuming that it's a fair coin. So, X0 among successes. So X of 0 successes among in trials is unusually high if the probability that X is greater than X of 0 is less than or equal to 5%, 0.05. In general, it is unusually high if the probability that X is greater than or equal to X of 0 is less than or equal to alpha, where alpha, the level of success, is some value between 0.01 and 0.10. X of 0 successes among in trials is unusually low if the probability that X is less than or equal to X of 0 is less than or equal to 0.05. In general, it is unusually low if the probability that X is less than or equal to x of 0, is less than or equal to some alpha, the level of significance, where alpha is some value between 0.01 and 0.10, the expected value. The expected value of a discrete random variable is denoted by capital E, parentheses, x, where x is the your random variable. It represents the average value of the outcomes. So we will define the expected value of a random variable x. Well, sometimes we'll also denote it by mu sub x, or if I know what the random variable is, I'll just say mu. It is defined as the sum x p of x for every outcome x corresponding to some member of your sample space. The variance of some random variable x will also be denoted by sigma squared sub x, or by sigma squared if it's evident what the random variable, the distribution is for your random variable x. The variance is defined as the sum of x minus mu quantity squared times p of x. It turns out that it's also equal to, after a little bit of arithmetic, the sum of x squared p of x minus mu squared, or, again, this is one of the most important formulas here that we'll be using in this course, the expected value of x squared minus expected value of x quantity squared. So we'll be using that a lot when looking at, well, trying to prove things involving variance. The standard deviation of x, sometimes also denoted by sigma sub x, or, well, just by sigma, is the square root of the sum of x minus mu squared p of x. It's equal to the square root of the sum of x squared p of x minus mu squared. It's equal to the square root of the expected value of x squared minus expected value of x quantity squared. So, why should we let the expected value equal this? Why should we define the expected value as this value? Why should we define the variance as this? Well, let me give you some reasoning why these make sense. And so, it really will be consistent with what we've done in the previous chapters. So, let me assume equally likely cases. It will basically be how we notice that in equally likely cases, that probabilities are the same as the relative frequency. And so doing that correspondence, then we will extend the idea of expected value of the mean and the variance using, well, the formula we get for equally likely cases, and then to extend it to the general case, even when we do not assume equally likely cases. So, the mean is equal to, well, for a frequency distribution, the sum of fx over n. N is a constant. So I can bring it inside the summation by the properties of summation. So this is equal to the sum of x times f over n. Well, f over n, the relative frequency, for equally likely cases, is just equal to the probability of X. So this is the sum of X times P of X. Therefore, even if I'm not assuming equally likely cases, I'll just define the mean to equal the sum of X P of X. Similarly, for the variance, for a frequency distribution, the variance was equal to the sum of fx minus mu squared over n. Since n is a constant, I can bring it inside the summation by the properties of summation. So this is equal to the sum of x minus mu squared times f over n. But again, f over n is just the probability of x. And so in the case of equally likely cases, we have that sigma squared is the sum of x minus mu squared times p of x. Let's just now agree that even in all, so then even when I'm not assuming equally likely cases, I will define the variance to be this formula. Let's show that it's also equal to this. Well, so assuming that the variance is the sum of x minus mu squared p of x, let's square this out. Well, by the special product formula, the perfect square trinomial formula, x minus mu squared is just x squared minus 2x mu plus mu squared. By properties of summation, this is the same as multiplying the p of x inside the parentheses and using the property of summation, the fact that summation is a linear transformation. I have this is equal to the sum of x squared p of x minus 2 mu, bringing the constant out in front of the summation, minus 2 mu sum of x p of x plus mu squared sum of p of x. Again, bringing the mu squared outside the summation. Well, the sum of p of x is just 1. So this last term is just mu squared. The sum of x p of x is just mu. This is minus 2 mu squared. Well, 1 mu squared minus 2 of them is minus 1 of the mu squared. And that's what you wanted to show. Similarly, the variance, sigma squared, is equal to, for a frequency distribution, n, sum fx quantity squared minus, sigma squared is equal to n, sum fx squared minus sum fx quantity squared all over n squared. Let's divide each of these two terms by n squared. One of the n's cancel. So this is the sum of fx squared over n minus, now, this quantity here is squared. So this is the same as sum fx over n quantity squared. And so, since n is the constant, I can bring it inside the summation. So by the property of summation, this is the same as the sum x squared times f over n minus the sum x times f over n quantity squared. This is equal to, well, the sum of x squared, the probability of x squared, minus the sum x p of x quantity squared, which is just equal to the expected value of x squared by this, minus the expected value of x quantity squared. So let's do the following. A shipment of 8 VCRs contains 2 defective ones. Two VCRs are selected at random. Let the random variable x be the number of defective VCRs in the sample. Determine the sample space and list the values of x. Oh, we already did that. Back here. There it is right there. Determine the sample space and list the value of X. Determine both the frequency distribution and probability distribution of X. Already did that. Determine the expected value and variance for the frequency distribution and probability distribution. Okay, so if you recall from like a few minutes ago, well, we're picking two VCRs. So the first one could be defective. Second one could be non-defective. So first one is defective or non-defective. And the second one is defective or non-defective. So the first one could be defective. Second one could be defective or non-defective. The first one could be non-defective, and the second could be defective or non-defective. So I have here the four situations for my sample space. I'm counting the number of defective VCRs. So there are 0 defectives, 1 defective, or 2 defectives. And we obtain this frequency distribution for them. Now it says to determine the expected value. Well, to determine my expected value, I added one additional column, the FX column, which I found by multiplying the first and second column to get the third column. 0 times 30, 0. 1 times 24, 24. 2 times 2, 4. And I added up the columns. 28, 56. Therefore, my mean, my expected value, sum fx over n, is 28 over 56. Let's figure out the variance. To figure out the variance, I need to attach yet an additional column, the fourth column, found by multiplying the first and third column. 0 times 0, 0. 1 times 24, 24. 2 times 4, 8. Add. Oops. Add. 32. And so I get n 56 times the sum fx squared 32 minus the sum fx 28 squared divided by n 56 squared. And so I get, well, after reducing this, 18 over 56. So let's do it now for a probability distribution. So for probability distribution, well, we got the same thing that we got here, except we divided by 56. So the probability distribution is this. So now I want to find the mean and the variance, the expected value and the variance. So to find the expected value, I attach a third column. I get the third column by multiplying the first and second column. 0 times 30 over 56 is 0. 1 times 24 over 56, 24 over 56. 2 times 2 over 56, 4 over 56. And now let's add. So I get 28 over 56. So the expected value is, well, the sum of this, which is 28 over 56. Now let's find the variance. So to find the variance, I attach a fourth column. To find the value in the fourth column, I multiply first and third column. 0 times 0, 0. 1 times 24 over 56, 24 over 56. 2 times 4 over 56, 8 over 56, and add 32 over 56. And so I get, well, the variance is 32 over 56 minus the 28 over 56, which is 1/4, which is 1/2 squared, which is 1/4, which is 14 out of 56. 32 over 56 minus 14 over 56 is 18 over 56. So notice the mean, 28 over 56, is the same. The variance, the 18 over 56, is also the same. So notice that for these situations, I get the same thing. As a matter of fact, the way that I compute them was the same. The only thing that made my life easier in this second situation is that in here, when I added up all these numbers in the second column here, this n here was 1. So if you had plugged in this formula here with the fractions and everything, not assuming that f here had to be an integer value. If you plug in 1 here for n, notice formulas are now the same. So this formula for the probability distribution is actually a little bit easier because you don't have to divide by, you don't have to deal with the number here because the number here is 1. But the way that we calculated it was the same way. We had to tax the third column to get mu, and then looked at both the third and fourth column to get the value of sigma squared. Okay, or the standard deviation of sigma. So, in a new project, the probability that the contractor will make $50,000 is 0.25. And he will make $30,000 is 0.3. That he will make $10,000 is 0.1. That he will break even is 0.1. And he will lose $5,000 is 0.25. Let the random variable x be the amount he makes in the completion of the project. Find the expected value of the random variable. So let's try to construct a probability histogram. So first, x here is the amount he will make, his profit. So he will make $50,000 with a probability of 0.25. And so he will make $50,000 with a probability of 0.25. He will make $30,000 with a probability of 0.3. He will make $10,000 with a probability of 0.1. He will break even, meaning he will not make any money, but he won't lose any money. And so he will make $0 with a probability of 0.1. So we have a 10% probability he will break even. There is a 25% chance, however, that he will lose $5,000. So I'll put a negative 5,000. So let's find the expected value. Multiply first and second column to get my third column. 50,000 times 0.25, 12,500. 30,000 times 0.3, 9,000. 10,000 times 0.1, 1,000. 0 times 0.1, 0. Negative 5,000 times 0.25, negative 1,250. Let's add these. So you're going to get 21,250. Therefore, the expected value, how much you expect to make at the end of this project, is $21,250. So that's how much you expect to make at the completion of this project. This is your expected value. Let the random variable X be the number of girls in 2 births. Find the mean, variance, and standard deviation. So I have here 2 births. So you can have a boy, 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 girl, girl, boy, or girl, girl. Each of them have a probability of 1/2 of getting a girl or a boy, getting a girl or a boy. And so I'm counting the number of girls. So let's say 0. So boy, boy, that means there are no girls. Boy, girl, girl, boy, there's 1 girl. Girl, girl, there are 2 girls. Let's figure out each of the corresponding probabilities. So boy, boy, 1/2 times 1/2 is 1/4. Let's find the probability of having 1 girl. Boy, girl, 1/2 times 1/2 is 1/4. Girl, boy, 1/2 times 1/2 is 1/4. 1/4 plus 1/4 is 1/2. Lastly, the probability of having 2 girls. 1/2 times 1/2 is 1/4. So now let's find the mean, the expected value. So let's attach a 3rd column, multiply the 1st and 2nd column to get the 3rd column. 0 times 0.25 is 0. 1 times 0.5, 0.5. 2 times 0.25, 0.5. Let's add these up. I get 1. Therefore, the expected value is 1. So you expect to have 1 girl after the 2nd birth. Let's determine the variance and the standard deviation. So let's attach the 4th column. To find the value in the 4th column, let's multiply 1st and 3rd columns. 0 times 0, 0. 1 times 0.5, 0.5. 2 times 0.5, 1. Add them up, 1.5. So let's figure out the variance. So I'll take this number, subtract from it. So the value you get by adding up everything in the 4th column minus the value you get by adding up everything in the 3rd column and squaring that. So 1.5 minus 1 squared is, well, 0.5. So the standard deviation is the square root of the variance, the square root of 0.5, 0.7071067,812. Given the following probability distribution, determine the mean and variance. So I'm given this probability distribution. Let's find the mean. So let's attach my 3rd column. 0 times 0 times 8 over 15, 0. 1 times 6 over 15, 6 over 15. 2 times 1 over 15, 2 over 15. Add these up, you get 8 over 15. Therefore, the mean, the expected value, is 8 over 15. Let's try to determine the variance. Multiply 1st and 3rd column. 0 times 0, 0. 1 times 6 over 15, 6 over 15. 2 times 2 over 15, 4 over 15. Add. So I get 10 over 15. Minus, so to find the variance, I'll take 10 over 15, subtract from it, 8 over 15 squared. And so 150 over 225 minus 64 over 225 is 86 over 225. And that is your variance. A discrete random variable can take all possible integer values from 1 to k each with a probability of 1 over k. A probability distribution whose probability is the same for each value of the random variable is called the uniform distribution. So this is a uniform distribution. Show that its mean and variance are, well, mu is k plus 1 over 2. Sigma squared is k squared minus 1 over 12. So let's recall that 1 plus 2 plus da 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 plus k is k times k plus 1 over 2. 1 squared plus 2 squared plus da 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 k squared is k times k plus 1 times 2k plus 1 over 6. This is the formulas that Gauss derived when he was 9 years old. So x could go from 1 to k, each of them having a probability of 1 over k. Let's attempt to determine the expected value. Let's multiply the first and second column to get the third column. 1 times 1 over k, 2 times 1 over k, 3 times 1 over k, dot, 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 k times 1 over k. Lastly, to determine the variance, let's multiply the first and third column to get the fourth column. 1 times 1 over k is 1 squared over k. 2 times 2 times 1 over k is 2 squared times 1 over k. 3 times 3 times 1 over k is 3 squared times 1 over k. Dot, 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 k times 1 over k is k squared times 1 over k. So let's add this. Well, I noticed that the 1 over k's are in common. So I'll just put the 1 over k, I'll factor it out. And I'll add 1 plus 2 plus 3 plus dot, dot, plus k. But that's just equal to k times k plus 1 over 2. Let's add up the fourth column. Well, again, there's a 1 over k in common. I'll write that out. And then I have a 1 squared plus 2 squared plus 3 squared plus dot, 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 k squared. And again, that's k times k plus 1 times 2k plus 1 all over 6. So let's determine the expected value. This, well, the k's cancel. So I just get k plus 1 over 2. Let's determine the variance, which is this last column minus the previous column squared. Well, the k's cancel, so I get k plus 1 times 2k plus 1 over 6. And as we've seen before, the k's cancel. So I just get k plus 1 over 2 squared. 2 squared is 4, k plus 1 finally squared is, well, k plus 1 times k plus 1. I have a k plus 1 in common. Let's bring it out in front. What remains is 2k plus 1 over 6, and it minus a k plus 1 over 4. Then we get a common denominator. Common denominator is 12. Multiply and divide by 2. So 2 times 2k plus 1 is 4k plus 2. 3 times, so again, to get a common denominator, I have to multiply this 4 by 3. 3 times k plus 1 is, well, 3k plus 3. And now let's simplify this. Since I have common denominator, I can subtract numerators. And so 4k minus 3k is 1k. 2 minus 3 is a negative 1. So I get k plus 1 times k minus 1 over 12. Well, again, by the special product formula, the product of the sum and difference of two terms is the difference of their squares. And so I get k squared minus 1 over 12. And that's what I wanted to show. So this is very similar to what we did back in chapter 2 or 3. Either chapter 2 or 3, I don't remember, when we had this same problem. Oh, it was chapter 3. In chapter 3, when we did this same problem back in chapter 3. Oh, except we didn't call this K, we called it capital M. So that was the only real difference. But of course, I also took some time to rederive these if you forgot them from junior high and high school when you first did it. Properties of discrete probability distributions. The expected value of a constant K. Actually, maybe I should. These are all the same, but they might look better here. Right here. Okay, so let's do this. Even bigger. Oops. Okay, but wait 1 second. This was. Okay, so. There we are, right there. Okay, so. Properties. Will you stop that? Properties of discrete probability distributions. Sometimes the computer goes a little wacky here. Actually, it's trying to update things. So it's updating some of the things that are off screen. That's why it was doing weird things. Okay, so now, properties of discrete probability distributions. So some of these we have shown previously for raw data. So now I'm going to show that these are true in general for any discrete probability distribution. As a matter of fact, I think almost all these statements are actually true for any probability distribution, both continuous and discrete. However, for the first few, well, what you'll see is for the first few, though, I'm going to be explicitly writing out some formulas, the definitions for a discrete probability distribution, so that well, the proofs are really just valid for discrete probability distributions, but with a very minor change, you can do it also for continuous probability distributions. We just don't happen to know. Well, we haven't looked at continuous yet, and you don't have the quote unquote knowledge, the prerequisite knowledge, to do it for the continuous. But they will work, and the proofs are basically the same if you happen to know something about things involving continuous distributions. Okay, so first off, let K be a constant. Then the expected value of a constant is just that same constant. So if your random variable is always equal to one value, then you expect that, well, what's the probability, what is the expected value that you expect for your random variable? Well, it's that constant. So the expected value of a constant K is that constant K. So let's prove this. Well, the expected value of K is the sum of x p of x. That's by definition, that's the expected value of x. But in this case, x only has one value, k. And the probability of k is 1. And therefore, well, k times 1 is k. So the expected value of k is k. Next, the expected value of x plus k is the expected value of x plus k. So if you happen to add some constant k to your random variable, then you just add that same constant k to your expected value. So the expected value, x plus k, is the sum of x plus k times the probability of x plus k. That's by definition of my expected value for a discrete probability distribution. But the expected value, but the probability of x plus k is the same as the probability of x. You can take any injective function of your random variable, and that will not change its probability. So let's multiply p of x inside the parentheses using the distributive property by the property of summation. This is the same as the sum of x p of x plus k times the probability of x. But k is a constant, so I can bring a constant out the summation. The sum of p of x is 1. The sum of x p of x is just the expected value of x. Therefore, I have shown that this is equal to the expected value of x plus k. And that's what I wanted to show. Next, well, the expected value of x minus k is the expected value of x minus k. And that's true for any constant k. We've actually already shown this in property 2. Just let k equal negative k, and then this works. But let me show it without using property 2. So the expected value of x minus k is the sum of x minus k times the probability of x minus k. But the probability of x minus k is the same as probability of x. Let me multiply p of x inside the parentheses. So this is the sum of x p of x minus k p of x by the property of summation. This is just equal to the sum x p of x minus the sum k p of x. Let's bring the constant k outside the parentheses. The sum p of x is 1 times k, is just your minus k. The sum of x p of x is just the expected value of x. And that's what I wanted to show. Next, the expected value of a constant k times your random variable x is just that constant k times the expected value of x. So, first off, let's suppose that k is equal to 0. So if k is equal to 0, then this is the expected value of 0. But the expected value of a constant is just itself 0. But 0 times anything is 0. So therefore, I've shown that this works when k is 0. So let's suppose k is not 0. Then the expected value of kx, by definition, is the sum kx times the probability of kx. But the probability of kx is just the probability of x. Let me bring the constant k outside the summation. So by the property of summation, this is just k times the sum of x p of x. But the sum of x p of x is the expected value of x. And that's what we wanted to show, that this is just equal to k times the expected value of x. Let me show again. Property 5 just follows from property 4. Just write multiplication, or just write division as multiplication by the reciprocal. And then this holds. And this follows from property 4. So the expected value of x over k is the expected value of x divided by k, so long as k is not 0. Again, I'm going to show this without using property 4. And of course, well, we're going to be using later in the chapter this form for several proofs, so it's good to write it out. The expected value of x over k is, by definition, the sum of x over k times the probability of x over k. But the probability of x over k is just the probability of x. By the properties of summation, I can bring the constant 1 out of k outside the summation. The sum of x p of x is just the expected value of x. And so this is equal to the expected value of x over k. And that's what you wanted to show. Next, the expected value of x plus y is the expected value of x plus the expected value of y. So let me show this. So the expected value of x plus y is the sum of x plus y times the probability of x plus y. So by distributive property, I can multiply p of x plus y inside the parentheses. So this is just the sum of x p of x plus y p of x plus y. By the property of summation, this is just the sum of x p of x plus y plus the sum of y p of x plus y. Let me fix y, and let's add up with respect to x. Well, the probability of x plus y is the same as the probability of x for any fixed value y. So this sum is the same as the sum of x p of x. Next, let me fix x. Then the probability of x plus y is just the probability of y for every value of x. Therefore, this sum is just the sum of y p of y. But the sum of x p of x is expected value of x. The sum of y p of y is expected value of y, and that's what you wanted to show. In general, I can show that this is true, that the expected value of the sum I equaling 1 to n of k sub I, x sub I, is just equal to the sum I equaling 1 to n of k sub I times the expected value of x sub I. So let's show this. So first, let me look at the initial case when n is equal to 1. So the expected value of the sum I equaling 1 to 1 of k sub I, x sub I, well, the sum from 1 to 1 is just k sub 1 times x1. But by the very first property that by the fourth property, sorry, it's the fourth property. By the fourth property, the expected value of k1, x1 is just k1 times expected value of x1, which I can write as the sum I equaling 1 to 1 of k sub I, expected value of x sub I. And that's what and so therefore, the initial case holds that this holds when n is equal to 1. Now let's try to show the induction case. So let's suppose that, I guess I'm just going to use the same n. Suppose that the sum I equal 1 to n of k sub I, x sub I is equal to the sum I equal 1 to n of k sub I, expected value of x sub I. Suppose that this works for some value n. I'll then show that this works. This formula works for n plus 1. So let's look at the expected value. I equaling 1 to n plus 1, k sub I, x sub I. Well, this is equal to the expected value of, the sum of the first n of these terms. The sum I equaling 1 to n, k sub y, x sub I, plus the very last term, k sub n plus 1 plus times x sub n plus 1. But by the previous thing that we proved here, I have that, well, the expected value of the sum of these random variables is the sum of the expected value of these random variables. So this is equal to, by property number 6, this is equal to the expected value of the sum I equal 1 to n of k sub I, x sub I, plus the expected value of k sub n plus 1 times x sub n plus 1. Well, by the induction hypothesis, we have that the expected value here of the sum I equal 1 to n, k sub I, x sub I, is just the sum I equal 1 to n of k sub I expected value of x sub I. And by property 4, we can bring the constant out in front of the expected value. So this is k sub n plus 1 times the expected value of x sub n plus 1. But, well, I can write this as the sum I equal 1 to n plus 1 of k sub I expected value of x sub I. But that is what I wanted to show, that this holds when I replace n by n plus 1. Therefore, by the principle of mathematical induction, the expected value of the sum I equal 1 to n, k sub I, x sub I, is just the sum I equal 1 to n of k sub I times the expected value of x sub I. And we've shown that this works for every natural number n. Next, we want to show that the variance of k is 0 for any constant k. So the variance of a constant is 0. And you certainly hope that's a true statement, that there's no if you have your random variables always equal to the same number, you certainly hope that it doesn't have any variance. So the variance of k, by definition, is just the sum of x minus mu squared times p of x, where in this case, x is k. So this is equal to k minus expected value of k, 1 squared, times the probability of k. Well, the probability of k is just 1. The expected value of k, by the very first property that we showed today, is k. K minus k is 0. 0 squared is 0. And so my answer is 0. And that's what I wanted to show. Next, the variance of x plus k is the variance of x. So if you add some constant to all of your values of your random variable, you don't change its variance. The variance, and what you'll notice is this is nearly identical to what we did back in chapter 3, the same proof. So the variance of x plus k is the sum of x plus k minus expected value of x plus k quantity squared times the probability of x plus k. Probability of x plus k is just the probability of x. The expected value of x plus k is the expected value of x plus k. Let's get rid of the parentheses. So this is just x plus k minus, I'll distribute the minus inside the parentheses, minus expected value of x minus k. K's cancel. So this is just x minus the expected value of x. But the expected value of x is mu, finding square, times p of x. But this, by definition, is the variance of x. And that's what you wanted to show. Well, the variance of x minus k is the variance of x. This follows directly from property 9. But again, I'll prove it without using property 9. So the variance of x minus k is the variance, is the sum x minus k minus expected value of x minus k quantity squared times the probability of x minus k. Well, the probability of x minus k is probability of x. The expected value of x minus k is the expected value of x minus k. Let's get rid of the parentheses. So this is x minus k minus the expected value of x minus and minus make that plus. Okay, k's cancel. Expected value of x is mu. So this is x minus mu squared times the probability of x. But this is just the variance of x, and that's what I wanted to show. Next, a very useful fact here that we're going to be using a lot is that the variance of x is the expected value of x squared minus expected value of x quantity squared. So the variance of x is equal to the sum of x minus mu squared times p of x by definition. But the probability of x is the same as the probability of x minus mu quantity squared. So this is equal to the expected value of x minus mu squared. Let's square this. And so by the special product formula, the perfect square trinomial formula, x minus mu quantity squared is x squared minus 2x mu plus mu squared. From property property 7, or property 7, sorry. So from property 7, I have that the expected value, the sum of these three, is just the sum of the expected values of these three. And from property 10, no. Oh, it is 7. By property 7. By property 7. Okay, so using property 7, I have that this is equal to expected value of x squared minus expected value of 2x mu plus expected value of mu squared. By property 1, the expected value of mu squared is mu squared. By property, I think that was 4. You take out the constants on the front. The expected value of 2x mu is just 2 mu expected value of x. Mu is just expected value of x. Mu is expected value of x. Expected value of x times expected value of x is expected value of x quantity squared. One of these minus 2 of them is minus 1 of them. So I've shown that this is equal to expected value of x squared minus expected value of x quantity squared. Next, the variance of k, a constant k, times x, is just k squared times the variance of x. So, the variance of kx is just, well, using property 11, is just the expected value of kx squared minus the expected value of kx quantity squared. K times x quantity squared is just k squared x squared. By property 4, I can bring a constant on the front. So the expected value of kx is just k times the expected value of x. By property 4, the expected value of k squared times x squared, I can bring the constant k squared on the front. It's just k squared times the expected value of x squared. I have k times the expected value of x quantity squared. So I can square each of these. So it's k squared times expected value of x quantity squared. I can factor out a k squared. So this is just k squared times the quantity, the expected value of x squared minus expected value of x quantity squared. But this thing in parentheses, by property 11, is just the variance of x. And so I have shown that this is equal to k squared times the variance of x, and that's what I wanted to show. 13. Well, again, property 13 will follow directly from property 12. But let me show it without using property 12. So the variance of x over k is the variance of x over k squared. So long, of course, as you're not divided by 0, so long as k here is not 0. So the variance of x over k is equal to the expected value of x over k quantity squared minus the expected value of x over k quantity squared. The expected value of x over k is just the expected value of x divided by k. X over k quantity squared is just x squared over k squared. By property 5, this is the same. This is equal to the expected value of x squared over k squared. By property 5, this expected value of the expected value of x over k is the expected value of x divided by k. Square this, so the expected value of x squared over k squared. This is k squared common. Let's factor that. Or we have a common denominator, so I can subtract numerators. So this is expected value of x squared minus expected value of x squared, which is just the variance of x over k squared. And that's what we wanted to show. The standard deviation of xk is equal to, or the standard deviation kx is the absolute value of k times the standard deviation of x. This follows directly from property 12. But let's show it this way. And so the standard deviation of a constant k times x is the square root of the expected value of k x quantity squared minus k, the expected value of kx, all quantity squared. By property 4, the expected value of kx is k times the expected value of x. K times x quantity squared is just k squared x squared. Again, by property 4, the expected value of k squared x squared is just k squared times the expected value of x squared. K times the expected value of x quantity squared is just k squared times the expected value of x squared. I can factor out that k squared. So this is just the square root of k squared times the expected value of x squared minus the expected value of x quantity squared. But this is just the variance of x. The square root of k squared is the absolute value of k. The square root of the variance is the standard deviation of x. And that's what I wanted to show. The standard deviation of x over k is the standard deviation of x divided by k, absolute value of k, so long as k is not 0. Again, this follows directly from property 14. But again, let's not use property 14. So the standard deviation of x over k is the square root of the expected value of x over k quantity squared minus the expected value of x over k, all quantity squared. Well, x over k quantity squared is x squared over k squared. By property 5, the expected value of x over k is the expected value of x over k. I can square that to get the expected value of x quantity squared over k squared. By property 5, the expected value of x squared over k squared is the expected value of x squared divided by k squared. I have a common denominator, is subtract numerators. So the expected value of x squared minus the expected value of x quantity squared. But that's just the variance of x. So I have the square root of the variance of x over k squared. The square root of the variance of x is the standard deviation of x. The square root of k squared is just the absolute value of k. And that's what I wanted to show. Property 16. If x and y are independent, then the expected value of x times y is the expected value of x times the expected value of y. Since x and y are independent random variables, then the probability of xy is just the probability of x times the probability of y. So the expected value of xy is the sum of xy times the probability of xy, which is just equal to the sum of x times y times the probability of x times the probability of y, since x and y are independent. Since y and p of y are constant in x, I can bring those out in front of the summation. And so, since the sum of x, p of x is constant, I can, constant in y, but it's just a constant. I can bring that out in front of the summation. So this is just the sum of the p, the sum of x, p of x, and what remains is the sum of y, p of y. But the sum of x, p of x is expected value of x. The sum of y, p of y is expected value of y. And that's what you wanted to show. Note, the covariance of x comma y will be defined as the expected value of xy minus the expected value of x times the expected value of y. So this sort of measures the amount of dependence on these two variables. If they're independent, then this is going to be 0. The covariance of x, y is equal to the expected value of the following product. The x minus the expected value of x times y minus the expected value of y. So let's try to show this. So let's look at the expected value of this product. X minus the expected value of x times y, expected value of y. Well, let's multiply this out. And so this would be the expected value of this product. So xy, x times the negative expected value of y, so minus x expected value of y. A negative expected value of x times y, so minus y expected value of x. Minus and minus become a plus expected value of x times expected value of y. So by property, whatever that was, 11 or something. Let me try to highlight that. There it is right here. Property 7. Property 7. So by property 7, I have the expected value is linear. So by property 7, I have that the expected value is linear. Therefore, the expected value of this is equal to the expected value of xy minus the expected value of x expected value of y minus the expected value of y expected value of x plus the expected value of expected value of x times expected value of y. Well, expected value of x is a constant. Expected value of y is a constant. Therefore, the expected value is, well, the expected value of this constant is a constant. Expected value of x times expected value of y. Expected value of x here is a constant, so I can bring it out in front by property 4. So this is equal to this. So expected value of y times expected value of x is expected value of x times the expected value of y. Next, again, since the expected value of y is a constant, I can bring it out in front by property of the expected, I can bring it out in front of the expected value by property number 4. So this is equal to, I'll bring this out in front, expected value of y times expected value of x. Well, these cancel here. The expected value of y times the expected value of x is the same as expected value of x times expected value of y. Multiplication is commutative. And so I've shown that this is equal to expected value of xy minus expected value of x minus expected value of y, which is just the covariance of x. Next, the variance of x plus y is the variance of x plus the variance of y plus 2 times the covariance of x, y. So let's look at this. The variance of x plus y is expected value of x plus y squared minus expected value of x plus y quantity squared. Well, by the special product formula, x plus y quantity squared is x squared plus 2xy plus y squared. By property, I think it's 7. Six, by property 6. By property 6, the expected value of x plus y is expected value of x plus the expected value of y. By the special product formula, the perfect square trinomial formula, the expected value of x plus the expected value of y quantity squared is expected value of x quantity squared plus 2 expected value of x, expected value of y plus expected value of y quantity squared. By property 9, by property 7, by property 7, the fact that the expected value is linear, we have that the expected value of x squared plus 2xy plus y squared is expected value of x squared plus 2 expected value of xy plus expected value of y squared. Now let's get rid of the parentheses here. So let's distribute the minus sign inside the parentheses. So this becomes minus expected value of x quantity squared minus 2 expected value of x expected value of y minus expected value of y squared. Let me group some things together. So let's group the expected value of x squared with minus expected value of x quantity squared. Let's group the expected value of y squared with minus expected value of y quantity squared. Let's group the 2 expected value of xy with the minus 2 expected value of x times y, expected value of y. Let me factor out the 2. So I get 2 times expected value of x times y minus expected value of x times expected value of y. This is the variance of x. This next term is variance of y, and this last term is the covariance of xy. So I've shown that the variance of x plus y is the variance of x plus the variance of y plus 2 times the covariance of xy. So therefore, and this is, well, we'll be using this a lot, if x and y are independent random variables, then the variance of x plus y is the variance of x plus the variance of y. This follows directly from 18. If X and Y are independent, then the covariance is 0. And so then 19 follows, but let's try not to use that. Let's try to do it independently. So the variance of X plus Y is the expected value of X plus Y quantity squared minus the expected value of X plus Y all quantity squared. By the special product formula, X plus Y quantity squared, the perfect square trinomial formula, is equal to X squared plus 2XY plus Y squared. By property 6, I think, I had the expected value of X plus Y is expected value of X plus expected value of Y. Next, by linearity, and I think that was 7, we have the expected value of these three terms is just the expected value of X squared plus 2 expected value of XY plus the expected value of Y squared. By the special product formula, the perfect square trinomial formula, the expected value of X plus the expected value of Y quantity squared is expected value of X quantity squared plus 2 expected value of X, expected value of Y, plus expected value of Y quantity squared. That we change all the signs inside the parentheses. So this is minus the expected value of X squared, minus 2 expected value of X, expected value of Y, minus expected value of Y squared. Since X and Y are independent, then the expected value of XY is expected value of X times expected value of Y. So these cancel. So I have here the expected value of X squared minus expected value of X quantity squared. I have expected value of Y squared minus expected value of Y quantity squared. But these first two terms is just the variance of X. These last two terms are the variance of Y. And that's what I wanted to show. 20. The variance of X is the expected value of the expected value of X minus the expected value of X quantity squared. So let's look at the expected value of the quantity X minus the expected value of X quantity squared. So by the special product formula, the perfect square trinomial, X minus the expected value of X quantity squared is just X squared minus 2 times X times the expected value of X plus expected value of X quantity squared. By property 7, the fact that the expected value is linear, we have this is equal to the expected value of X squared minus 2, minus the expected value of 2X expected value of X plus the expected value of the expected value of X squared. Well, the expected value of X quantity squared is a constant. So the expected value of a constant by property 1 is just that constant, expected value of X quantity squared. By property 4, I can bring the constants out in front of the expected value. So I'll bring the constant 2 and the expected value of X out in front of the expected value. The expected value of X times the expected value of X is the expected value of X quantity squared. One of these minus 2 of them is minus 1 of the expected value of X quantity squared. The expected value of X squared minus expected value of X quantity squared is just the variance of X. And that's what I wanted to show. Oh, good.